To the boson precise, the number n of T1 and T2 of a point Ti in an interval of T1 and T2 of length T equals to T2 to minus T1 is a boson random variables with parameter lambda t, and the probability of Tn of T1 and T2 equals to K and equal to that, and the interval T1, T2, and T3 and T4 are non-overlapping. So we can know that n T1, T2, and T3, T4 are independent. So we can make a stochastic precise xt equals to n of n and t, because xt is a Poisson random variables with parameter lambda t. So we know that the mean of xt equals to lambda t, and the autocorrelation are t and t1 and t2. When t larger than t2, it equals to lambda t2 plus lambda square and t1, t2, and t2, and when t1 less than t2, it equals to lambda t plus lambda square t1 and t2. And to Poisson increment, we make a yt equals to xt plus c minus xt over c, and we make sure that xt is a Poisson precise and c is a fixed number. The probability of yt equals to n over c equals to probability of xt plus c minus xt equals to n, and it equals to that, and the mean of yt equals to lambda, and the autocorrelation yt1 and t2 we can get if t1 plus c less than t2, it equals to that, and t1 plus c larger than t2, it equals to lambda square, and then we can figure out normal precise, and a precise xt is called normal if the random variables xt1 to xtn are joint normal for any t, and t1 to tn, and x1 to tn are joint normal. We can get its distribution only depends on mean of x1. And we get to the second question. First, we need to know about WSS precise. Stochastic precise XLT is called WSS if its mean is constant. So we can get it equals to that, and its autocorrelation depends only on T1 minus T2. So we can get this formula, and second, we need to know about independent increment precise. So if the increment xt2 minus t1 and xt4 minus t3 of a precise xt is uncorrelated, so it's independent for any t1, t2, t3, t4, then we decide that xt is precise with independent increments. That's the definition of independent increment precise. And then we need to know about macro precise. If t1, t2, and t1 larger than t2, and so on. So we know that the probability of t1 xt1 less than x1 and xt2 equals x2 and so on, and we can get the probability of xt1 less than x1 and xt2 to so on, so the xt equals to the number of packets at t. So for macro precise ft1 t2 x1 x2 t1 t2 enough to like we know about the whole statistic. Then is the SSS. A stochastic precise xt is called SSS. Strict sign stationary precise if it's a stochastic properties are invariant to a shift of its origin, and this means that the precise xt and xt plus c has the same stochastics for any c. And then we need to know about white noise. We said NT and NT1 and NT2 are uncorrelated, and T1 doesn't equal to T2, so we can get these formulas, and we know that about that CNT1 and T2 equals to QT1 and T2 T1 and minus T2, and the precise YT is white noise if it's very VTI and VTJ are uncorrelated for any T1, TI and TJ, and TI doesn't equal to TJ.